Let's do an example of solving a parallel circuit. So in this example, it tells you three things. It tells you the total voltage, 20 volts. I'm going to write that in here because that's going to help me a little bit. 20 volts. It tells us R1, which is 20 ohms. And it tells us R2, which is 30 ohms. And then we are asked for the total current, the current through each of the resistors, and the voltage drop for each of the resistors. So I have two possible circuits, two possible paths for electrons to follow. So it says that current is traveling this way, and that's true. Conventional current travels that way, but it doesn't matter. You can consider it going either direction. I'm going to say that all the time because no matter how many times I say it, people get confused about where current is at any given point in time. But time does not matter. You can consider that the whole thing is filled with electricity the moment it is connected. Okay? And so we've got a path like this. The green path. And we also have the red path. And because there are two different paths for electricity to follow, this would be a parallel circuit. In fact, R1 and R2 are said to be connected in parallel because they are not part of the same path. So if you have two components or two resistors that are not part of the same path, one single electron couldn't possibly go through both of them in one circuit, then you have a parallel set of components. So all we have in this circuit are two parallel components. And that means that this 20 volts has to be used up in each path. So the green path has to use the 20 volts and the red path has to use the 20 volts. And so we already know that the voltage drop through each of these resistors has to be 20 volts, right? That's one single path. This is the only component in the green path, and so it must, V1, drop 20 volts. Okay, same thing with R2. It's the only component in that path, and so it must drop the entire 20 volts. Now we can look at I1 and I2. So I1, the current through this branch, is going to be V equals IR. We know the V, we know the R, and so we can figure out the I just through algebra. So V1 equals I1 R1. We know that V1 is 20 volts. We're looking for I1. And we know R1 is 20 ohms. And so when you divide by 20, you get I is 1 amp. So the current going through the first resistor, R1, is going to be 1 amp. I2, we can do exactly the same thing. We're just going to do V2 equals I2 R2. V2 is also 20 volts. I2 is what we're looking for, and R2 is 30 ohms. And so when we do 20 divided by 30, that's 2/3, or 0.6 repeating. And so I'm going to write in 2/3 of an amp, because fractions are your friends, but you are very welcome to just write in 0.67, that's totally fine. 2/3 of an amp is I2. And finally, total current. So this is governed by Kirchhoff's junction rule, or Kirchhoff's current rule. And so that says that the branch currents add up to the total current. Or if we were looking at this junction over here, the currents coming into that junction have to be equal to the currents leaving that junction. Or you can look at it the other way around. If the current is going this way, the current entering that junction has to be equal to the sum of the currents leaving that junction. And so the two currents coming in are 1 amp and 2/3 of an amp, and so together they give us a total current of 1 2/3 amps. Or, if you like it better, 1.67 amps. And that gives us the whole thing. Now, we could also figure out a whole bunch of other stuff, like what is the equivalent resistance? And the equivalent resistance, because these are in parallel, uses the parallel rule. And so the parallel rule goes like this. 1 over Req, 1 over the equivalent resistance, is equal to 1 over R1 plus 1 over R2. R1 is 20, R2 is 30, and so 1 over the equivalent resistance is equal to 1 over 20 ohms plus 1 over 30 ohms. And when you add those up, you get 5/60ths or 1/12. So 1 over the equivalent resistance of the circuit is equal to 1 over 12. And so now, to get the equivalent resistance, now we can flip this upside down. We can do the reciprocal. And so the equivalent resistance of this circuit is going to be 12 ohms. Now, to make sure that that's true, that needs to be smaller than any of the individual branch resistances. And so R1 has a resistance of 20 ohms, R2 has a resistance of 30 ohms. 12 is smaller than both of those, so it fits at least that criteria. Let's try one more here that isn't actually purely parallel, but it might give us a good example of how to do it anyway. So we are told nothing about the source at all. We are told that the voltage drop for resistor 1 is 8 volts and its resistance is 4 ohms. We're told the resistance of resistor 3 and we're told the resistance of resistor 2. So what we need to recognize first of all is what the relationship is between the different resistors in this circuit. So resistor 3 and resistor 2 are in series with one another. Okay, let's just draw out paths here and hopefully that will be helpful. So here's path number 1. That's one path for electricity to follow. And here is path number 2. And notice how path number 2 includes both resistor 2 and resistor 3. That means that if electricity is flowing through resistor number 2, or if a single electron goes through resistor number 2, it must also go through resistor number 3. And that means those two are in series with one another. And these two resistors together are in parallel with resistor number 1 because they are in different branches. If an electron goes through resistor 1, it cannot also go through resistor 2 and 3. Okay, so let's just see if we can fill in some blanks here. The first thing that I see is that for resistor number 1 over here, it tells us V and R. And because we have Ohm's law, V equals IR, if we're given any two pieces for a particular component or for the whole collective, then we can solve for the third one. So that's the first thing I'm going to do. And we're going to find that when we fill in one blank, often that leads us to filling in some other blanks. It's a puzzle. And so let's go V1 equals I1R1. And we get 8 volts is equal to I1 times 4 ohms. And so when we divide by 4, we get 2 amps is current number 1. Now I'm going to put that directly in here so that I don't lose track of that piece of information. So now I know that I1 is 2 amps. Okay, now if I knew how much current there was in total, then I could figure out the current going through these two, and then solving the rest of this would be really easy. Wouldn't be a big deal. But I don't know that. So what else can I do? Well, I have all the resistances. So I have this 4 ohms, 6 ohms, and 2 ohms. And so I can, if I have all the resistances, figure out the equivalent resistance. Now, I can't just add them up using the parallel rule, because R3 and R2 are not in parallel with each other. They together are in parallel with R1, but they are not in parallel with each other, so I can't just use the parallel rule. It means that first I have to deal with these two, whose relationship is a series relationship. Okay, and so I'm going to add up the resistance for that branch, and then use that branch resistance in parallel with R1. Okay, and so this is R3, this is R2. When I add them up, I get 8 ohms altogether. Okay, so the total resistance of this branch, or R23, that's what I'm going to call it, is 8 ohms. So I know the total resistance of that branch. And then to figure out Req, which I'm going to go down here, Req, or 1 over Req, is equal to 1 over 4, because that's resistor 1, plus 1 over 8. And so the equivalent resistance of the whole circuit, when I add these two things up, this is 2 over 8 plus 1 over 8, which is 3 over 8, and then I need to flip it upside down, which gives me 8 over 3. 8 over 3 ohms. Okay, now I'm going to change this to a decimal just so that I can be consistent using decimals throughout the whole thing. And that equals 2.67 ohms. So I'm going to put that in here, 2.67 ohms. The next thing I'm noticing here is that this branch, the green path, has a total resistance of 4 ohms, and the red path has a total resistance of 8 ohms. The red path has twice the resistance that the green path has. And that means that half the current is going to travel through the red path. Okay, so resistance is resistance to current flow. And if you have twice the resistance, you'll have half the current. And so if this has 2 amps of current flowing through the green path, half of that is going to travel through the red path. And so then we can say that I23, or the current traveling through resistor 2 and resistor 3, is going to be half of the current traveling through resistor 1, which is 1 amp. So that's the current in the red path. Now, that means that the current traveling through resistor 2 is going to be 1 amp, and the current traveling through resistor 3 is going to be 1 amp, because any current that enters this branch has to go through both of those resistors. So I2 is going to be 1 amp, I3 is going to be 1 amp. And now we can fill in the total current, because the junction rule tells us that the current entering this junction needs to be the same as the current leaving this junction. And so we have 1 amp in the red path and 2 amps in the green path, and so together they are going to give us 3 amps. So the total current in the circuit is 3 amps. Now I can get VT. So Ohm's law says that the total voltage is equal to the total current times the total resistance. And I'm going to use RT here just to be consistent with my subscripts, but RT is Req. It's equivalent resistance for the circuit. So VT is equal to 3 amps times 2.67 ohms. This is a 2. And so the total voltage is equal to 8 ohms. 8 volts, I should say. And this makes sense because we know that each branch must drop the entire voltage, or each path must drop the entire voltage. So this green path, we knew from the very beginning that it drops 8 volts of potential. And so if the green path drops 8 volts of potential, that means the entire thing is 8 volts of potential, because that's one entire path. And so we had to jump through some hoops to get all the way over here, but we actually could have filled that in from the very beginning. So this is 8 volts. And because this branch drops 8 volts, we know that this entire branch has to drop 8 volts as well. But not each of these resistors. Remember that in series, the total voltage drop is equal to the sum of all the voltage drops. And so V2 plus V3 is going to be 8 volts, but they won't each be 8 volts. Now, we can figure out how much each of those is using V equals IR, because we have I and R for both of them. We could also figure out how much it is using algebra, because this R2 has 3 times the resistance of R3, and so it's going to drop 3 times the voltage. Okay, so we could also do it that way. We know that the total is 8 volts, this one is 3 times the other one, and so you could figure it out using algebra. I'm going to use V equals IR for one of them, and then figure out the other one pretty quickly. So I'm going to go V2 equals I2 times R2. V2 is equal to the current going through I2, which is, or the current going through R2, which is 1 amp, and its resistance, which is 6 ohms. And so that gives me a voltage drop, or a potential difference, across that resistor of 6 volts. And so if 6 volts is dropping there, the rest of the 8 volts needs to be dropping over here. And so that's 2 volts. And we can see that if we would use V equals IR for this resistor as well, I times R, 1 times 2, is in fact 2 volts as well. And so that gives us the same answer. So consistency via the many methods of figuring out all of these pieces is important. You should always get the same answers.